Next, we'll work some examples. On a typical day, a nurse encounters several situations involving measurement. State the name and type of measurement indicated by the units in each of the following. A patient has a temperature of 38.5 degrees C. A degree Celsius is a unit of temperature. A physician orders 1.5 grams of sulfarazine for injection. A gram is a unit of mass. A physician orders 1 liter of sodium chloride solution to be given intravenously. A liter is a unit of volume. A medication is to be given to a patient every 4 hours. An hour is a unit of time. Next, we'll state the names and types of measurements for an infant that is 54.6 centimeters long with a mass of 5.2 kilograms. A centimeter is a unit of length. A kilogram is a unit of mass. Sample problem 2.2, measured and exact numbers. Identify each of the following numbers as measured or exact and give the number of significant figures in each of the measured numbers. 0.170 liters. This is a measured number that has 3 significant figures. B, 4 knives. This is an exact number. When counting objects, that is an exact number. C, 6.3 times 10 to the minus 6 seconds. This is a measured number with 2 significant figures. D, 1 meter equals 100 centimeters. This is an exact number because it is a conversion factor within a system of measurements. Study check 2.2. Identify each of the following numbers as measured or exact and give the number of significant figures in each of the measured numbers. A says 0.02080. Let's write that number to the side and examine it further. 0.02080. Notice that these first 2 zeros are placeholders. The significant figures are the number behind the first non-zero digit, 2080. All of these are significant. So there are 4 significant figures. 5.06 times 10 to the 4th hours. We have 3 significant figures. C says 4 chemistry books. This is a counted number and therefore there are unlimited number of significant figures. Next we have 85,600. Notice that these trailing zeros are simply placeholders and the number is technically ambiguous, but we're only certain of 3 significant figures. So this is a measured number with 3 significant figures. Next, we have some rounding examples. Round off or add zeros to each of the following measurements to give 3 significant figures. A, 35.7823. Where are 3 significant figures? The last significant figure would be at the 7, so in the tenths place. So we need to round the 7. We look to the right of the 7 and identify an 8. 8 is 5 or more, and so we're going to round the 7 up to the next digit. So our final answer will be 35.8. Now let's work problem B. Problem B is 0.0026217 liters. Notice that the first 2 zeros behind the decimal place are just placeholders. So all of these other are non-zero digits. We need to round to 3 significant figures. The third significant figure would be here, so we look to the right of it. We identify a 1, which is 4 or less, and therefore we're going to keep the preceding digit. So the final answer will be 0.00262 liters. The next number C is 3.8268 times 10 to the 3rd grams. All of these are non-zero digits, and therefore we need to identify the third significant figure, which would be the 2. It's in the hundredths place. We look to the right of it and we identify a 6. 6 is 5 or more, and so we're going to round the 2 up 1. So our final answer will be 3.83 times 10 to the third grams. The next one is 8 seconds. Now, 8 seconds doesn't have three significant figures, but there's an implied decimal place right behind the 8. So for example, if you get this number on your calculator, but you need three significant figures, you can add two zeros to account for the extra two significant figures. So our answer is 8.00 seconds. Let's work some multiplication and division problems. A says 56.8 times 0.37. If we put that into the calculator, 56.8 times 0.37, we see that we have three significant figures in the first value and two significant figures in the second value. Since we're multiplying and dividing, we're limited by the least number of significant figures. Our calculator displays 21.016, and we need to round that to two significant figures, which would be the 1 here would be our last significant figure. So we look to the right of it, which is 4 or less, it's 0. So we're going to round this number to 21. We keep the number to the left, the 1, the same. We keep the last significant figure the same because the number to the right of it is 4 or less. So our final answer would be 21. The next problem, B, states 2.075 times 0.585. Then we can hit equals and the divided by button, and we get 8.42. And then we hit equals and divided by 0.0245. So we see that we have four significant figures, three significant figures, three significant figures, and three significant figures. So we're limited to three significant figures in our final calculation. Our calculator displays 5.8843133345, and we have three significant figures, so that would be the last significant figure would be the 8 here. We look to the right of it and we see a 4. 4 is 4 or less, and therefore we keep the last significant figure the same, and our final answer then would be 5.88. Problem C says divide 25.0 by 5.00. Each of these numbers has three significant figures, and therefore we're going to be limited to three significant figures in our final calculation. If we put 25.0 into the calculator and we divide by 5.00, the calculator displays 5. Now, we need three significant figures, and we have an implied decimal point after the 5, so we just add two zeros to give us the final three significant figures that we need. Let's work a few more examples with that. Problem A says 45.26 times 0.01088. Notice that each of these entries has four significant figures. So when we put that into the calculator, we need to round our answer to 0.4924. B is 2.6 divided by 324. If we put that into the calculator, we need to round to two significant figures, and therefore our answer could be displayed as 0.0080 or 8.0 times 10 to the minus third. For C, we have two significant figures, three significant figures, and two significant figures. So we put that into the calculator, 4 times 8 divided by 16, and we need our final answer to have two significant figures. The calculator will display 2. We have an implied decimal point, so we need to add a 0 behind it. Next, we'll work some problems with addition and subtraction. Remember, generally with addition and subtraction, we're limited by the value with the least number of decimal places. However, this example is a bit unusual. To work this example correctly, we need to consider the place value for each of the digits in each of the values used in the calculation. So we have here 104 plus 7.8 plus 40. If we line all these values up, we'll see that 104 has 0 decimal places, 7.8 has 1 decimal place, and 40 has 0 decimal places. So you might be tempted to just round this to no decimal places. So in other words, if the calculator display is 151.8, you'd be tempted to round this to 152. But since the last significant value for these digits is like this, let's look at it differently. The last significant value for 104 is in the ones place, and for 7.8 is in the tenths place, and for 40 is in the tens place. We're limited to our answer having the last significant figure in the tens place. So since our calculator display is 151.8, we need to round our final answer to 150. Now again, this is an unusual problem, and you generally won't see problems of this nature. Most of the time you'll be presented with a problem something like this: 153.247 minus 14.82. We have 3 decimal places in the top answer and in the top value and 2 decimal places in the bottom value. When we subtract, our calculator display is 138.427. Since we have 2 decimal places in the value with the least number of decimal places, we're going to round to 2 decimal places. So our final answer would be rounded to the hundredths place. We look to the right of it and we observe a 7. Since 7 is 5 or more, we're going to round that 2 up to the next digit. So our final answer will be 138.43. Let's work a few more examples. A, down here in study check 2.5, asks us to add 82.45 plus 1.245 plus 0.00056. When we put these numbers into the calculator, we observe the calculator display is 83.69556. Notice that the first value has 2 decimal places, the second has 3, and the third has only 2 decimal places. So we need 2 decimal places in our final answer. So we need to round this value to 83.70 because the last digit is going to be a 9. We look to the right of it, which is 5 or more, so we're going to round this digit up. When we round 9 up to 10, we have to carry a 1, and that gives us our final answer of 83.70 with 2 decimal places. Notice that when adding and subtracting, you can actually gain or lose significant figures, and this is an example of that. B says 42. Notice that when adding or subtracting, it's possible to gain or lose significant figures, and this is an example of that. Problem B says 4.259 minus 3.8. We put that number into the calculator and it displays 0.459. Now, Each of these values has the following decimal places. The first value has 3 and the second value has 1. So we'll need to round our final answer to one decimal place. The first decimal place that's significant is a 4. The 4 is in the first significant decimal place. So we look to the right of that and we observe a 5, which is 5 or more. So we're going to need to round that 4 up, and that will give us 0.5 as our final answer. Notice we don't have anything left in the ones place, and this is because when we subtracted, the value in the ones place went away. An endoscopic camera has a width of 1 millimeter. Complete each of the following equalities involving millimeters. 1 meter is equal to how many millimeters? We see that if we look at our chart, 1 meter is 1,000 millimeters. 1 centimeter is 10 millimeters. What is the relationship between millimeters and micrometers? 1 millimeter is 1,000 micrometers, and 1 liter is 100 centiliters. Write the following equalities and conversion factors and identify each number as exact or give the number of significant figures. A says, a medication that Greg takes for his high blood pressure contains 40 milligrams of propanolol in one tablet. Let's make a conversion factor out of that. We see that we have 40 milligrams of propanolol in one tablet, or one tablet is 40 milligrams of propanolol. The 40 milligrams is measured and the tablet is exact. So we don't need to limit our significant figures by the one tablet, but we would be limited to 2 significant figures for the 40. And notice that there's a decimal place behind the 40, and that means that the 0 is significant. Problem B says cold water fish, such as salmon, contain 1.9% omega-3 fatty acids by mass. So 100 grams of salmon is equal to 1.9 grams of omega-3 fatty acid. Because remember, percentage means that amount per 100. And here we're measuring in grams. So we can say that we have 1.9 grams for every 100 grams of fish. So that's 1.9 grams of omega-3 fatty acids per 100 grams of salmon, or 100 grams of salmon per 1.9 grams of omega-3 fatty acids. The 1.9 grams is measured and the 100 grams is exact. Next, we see that the U.S. Environmental Protection Agency has set a maximum level of mercury in tuna at 0.5 parts per million. So that means that our value is milligrams per kilogram. So 0.5 milligrams of mercury per kilogram of tuna. So 0.5 milligrams of mercury per 1 kilogram of tuna, or 1 kilogram of tuna per 0.5 milligrams of mercury. The 0.5 milligrams is measured and the kilogram is exact. Levsin, used to treat stomach and bladder problems, is available as drops with 0.125 milligrams of Levsin per 1 milliliter of solution. Let's write a conversion factor for that. So 1 milliliter of solution is 0.125 milligrams of Levsin. So we can write that as 0.125 milligrams of Levsin per 1 milliliter of solution. Or 1 milliliter of solution is 0.125 milligrams of Levsin. So the 0.125 is measured and the 1 milliliter is exact. So we're limited to 3 significant figures in this measurement. The EPA has set a maximum level of cadmium in rice as 0.4 parts per million. Remember, parts per million is milligrams per kilogram. So we have 0.4 milligrams of cadmium per 1 kilogram of rice, or 1 kilogram of rice contains 0.4 milligrams of cadmium. The 0.4 is measured and the kilogram is exact. So we're limited to 1 significant figure from the 0.4 in the milligrams. Let's use some conversion factors. Greg's doctor has ordered a PET scan of his heart. In radiological imaging, doses of pharmaceuticals are based on body mass. If Greg weighs 164 pounds, what is his body mass in kilograms? In this problem, we need to take 164 pounds and convert it to kilograms. So we're starting with 164 pounds. We know that 2.20 pounds is 1 kilogram. So we have a conversion factor, 2.2 pounds per kilograms. So we need to put the pounds on the bottom in order to cancel pounds. 2.20 pounds is equal to 1 kilogram. So pounds cancels and we're left with kilograms now. And if you multiply 164 by 1 and then divide by 2.20, we get 74.5 kilograms. Study check 2.8 states a total of 2,500 milliliters of a boric acid antiseptic solution is prepared from boric acid concentrate. How many quarts of boric acid have been prepared? Notice the number 2,500 doesn't have a decimal point behind it. That means that this is limited to two significant figures. So we have 2,500 milliliters. If you look at a conversion chart, you'll see that there are 946 milliliters in a quart. 946 is a measured number. We can use that as a conversion factor, and we need to put the 946 on the bottom. So we have 946 milliliters so that we can cancel milliliters per 1 quart. To put this in the calculator, we put 2,500 and divide by 946. Our calculator displays a number of 2.642706. Now, we need to round to two significant figures because we're limited to two significant figures from the 2,500. And the 6 would be our second significant figure. We look to the right of it and we see that it's 4 or less, so we keep the 6 as is and round our number to 2.6 quarts. Next, a vial contains 65 milligrams of phenobarbital per 1 milliliter of solution. How many milliliters are needed for an order of 40 milligrams of phenobarbital? Notice there's a decimal place here, and that means there are two significant figures in the 40 milligrams. So let's work this problem. We're starting with 40 milligrams, and we need to convert that 40 milligrams to milliliters of solution. We can use the 65 milligrams per milliliter as a conversion factor. So we have, let's put milligrams in. We have 40 milligrams of phenobarbital, and we know that the solution contains 65 milligrams per milliliter, or rather we want 40 milligrams, and we know the solution contains 65 milligrams per milliliter. Now milligrams cancels and we're left with milliliters. If we put this number into the calculator, our calculator displays 0.61538 milliliters. We need to round this to two significant figures because the 40 and the 65 are limited to two significant figures, and both of those are measured values. Our second significant figure is a 1. If we look to the right of it, it's 5 or more, and so we'll round our final answer to 0.62 milliliters. Greg has been diagnosed with diminished thyroid function. His doctor prescribes a dosage of 0.150 milligrams of Synthroid to be taken once a day. If tablets in stock contain 75 micrograms of Synthroid, how many tablets are required to provide the prescribed medication? We're starting with milligrams. We have 0.150 milligrams of Synthroid. We need to first use a metric conversion factor to convert milligrams to micrograms. Once we have micrograms, we can use the clinical factor to convert micrograms to numbers of tablets. So notice that 1 milligram is equal to 1,000 micrograms. That gives us our metric conversion factor of 1 milligram per 1,000 micrograms. And the problem tells us that one tablet contains 75 micrograms of synthroid. That's our second conversion factor. One tablet per 75 micrograms, or 75 micrograms per one tablet. Starting with 0.150 milligrams of synthroid, we multiply times 1,000 micrograms per milligram, and milligrams cancels, and then we multiply by 1 tablet per 75 micrograms of synthroid, and the micrograms cancels. Our final answer for this problem is 2 tablets. Study check 2.9, problem A says, a bottle contains 120 milliliters of cough syrup. If 1 teaspoon is given 4 times a day, how many days will elapse before a refill is needed? We see that 1 teaspoon contains 5 milliliters, and so we can really just leave the teaspoon out of this calculation because we already know that we need 5 milliliters per what? Per dose. So this problem is a little bit tough because we need to understand that we need 5 milliliters of cough syrup per dose. And 1 dose is given 4 times a day. So we're given 4 doses per 1 day. Okay, so we're starting with 120 milliliters of cough syrup. We need 5 milliliters per 1 dose. We weren't asked to convert that into teaspoons, and we didn't start with teaspoons, so we can ignore the teaspoons. But we need to understand that we're given 4 doses per 1 day. We were asked to find how many days elapsed before we need a refill. So let's notice that milliliters cancels, doses cancel, and we're left with days. If we multiply 120 times 1 times 1, and then divide by 5, and then divide by 4, we see that we can wait 6 days, or we can make it 6 days, before we'll need a refill. Patient is given a solution containing 0.625 grams of calcium carbonate. The chemical formula for calcium carbonate, by the way, is CaCO3. We'll just use that as an abbreviation. If the calcium carbonate solution contains 1,250 milligrams per 5 milliliters, how many milliliters of the solution were given to the patient? We see that we're starting with grams, not milligrams, but we have our conversion in milligrams per 5 milliliters. So we'll need to do a two-step problem. First, we'll convert grams to milligrams, and then we'll convert milligrams to milliliters. We'll use a metric conversion to convert grams to milligrams because we know that 1,000 milligrams is 1 gram. And we'll use our problem conversion factor here, given conversion factor, to convert milligrams to milliliters. We know in this case that 1,250 milligrams is in every 5 milliliters of solution. So let's go ahead and get started with this problem. So we're starting with 0.625 grams of calcium carbonate, CaCO3. We have 1,000 milligrams per 1 gram, and 5 milliliters of solution contains 1,250 milligrams. Now we see that Grams cancels, milligrams cancels, and we're left with milliliters. So our final answer is 2.5 milliliters. Using percent as a conversion factor. A person who exercises regularly has a 16% body fat by mass. If this person weighs 155 pounds, what is the mass in kilograms of body fat? We'll need to convert pounds first to kilograms, and then we can use our percentage factor to convert kilograms of body mass to kilograms of body fat. We know that 1 kilogram of body mass is equal to 2.2 pounds of body weight, and 100 kilograms of body mass is equal to 16 kilograms of body fat. And that's because, remember, percentage means parts per hundred. And therefore, if we have 16% body fat by mass and our units are in kilograms, we'll have 16 kilograms of body fat per 100 kilograms of body mass. So we can use that as our second conversion factor. So let's go ahead and get started. We're starting with 155 pounds of body weight. We multiply by the conversion factor, 2.20 pounds per kilogram. We need to put the pounds on the bottom so that pounds cancels. Then we multiply by the second conversion factor, 16 kilograms of body fat per 100 kilograms of body mass, so that kilograms of body mass cancels and we're left with kilograms of body fat. So that gives us 11 kilograms of body fat. A package contains 1.33 pounds of ground round. If it contains 15% fat, how many grams of fat are in the ground round? So we're starting with 1.33 pounds of ground round. We need to convert first pounds to kilograms. And we see in a previous example that 2.20 pounds is 1 kilogram. So 2.20 pounds of ground round is 1 kilogram of ground round. And it's 15% fat. So that means there's 15 kilograms of fat per 100 kilograms of ground round. So we were asked to find how many grams of fat are in the ground round. So let's put in our next conversion factor. So that is 100 kilograms of round per 15 kilograms of fat. So now we have kilograms of fat, but we were asked to find how many grams of fat are in the ground round. We need to convert kilograms to grams. There are 1,000 grams in 1 kilogram. So let's examine our units now. Pounds cancels, kilograms of round cancels, kilograms of fat cancels, and now we have grams of fat. So to get the final answer to this problem, we'll multiply 1.33 times 1 times 15 times 1,000, and then hit equal, and divided by 2.20, and then equals, and divided by 100. So our final answer then becomes our final answer is 180 grams of fat. A cream contains 4% lidocaine by mass. Now, what does that mean? That means 4 grams of lidocaine per 100 grams of cream. Okay. If a patient uses 12 grams of cream, how many milligrams of lidocaine are used? So we're starting with 12 grams of cream, and we want to convert to milligrams of lidocaine. So first we're going to convert grams of cream to grams of lidocaine, and we'll use our percentage conversion factor to do that, and then we'll convert grams of lidocaine to milligrams of lidocaine, and I'm just abbreviating lidocaine as LID. So let's get started. We have 12 grams of cream. There are 4 grams of lidocaine in 100 grams of cream. Now we have grams of lidocaine, but we were asked to find milligrams of lidocaine, and so 1,000 milligrams is 1 gram. And so we're going to multiply 12 times 4 times 1,000 and then divide by 100. And we see that grams cancels, grams of cream cancels, grams of lidocaine cancels, and we're left with milligrams of lidocaine. To calculate this, we'll say 12 times 4 times 1,000 divided by 100, and we get 480 milligrams of lidocaine. Let's work some density problems. High density lipoprotein is a type of cholesterol sometimes called good cholesterol that's measured in a routine blood test. If a 0.258 gram sample of HDL has a volume of 0.215 milliliters, what is the density in grams per milliliter of the HDL sample? Remember, density is mass over volume. So in this problem, we just need to divide the mass by the volume. Our mass is 0.258 grams and our volume is 0.215 milliliters. So we divide 0.258 grams divided by 0.215 milliliters and we get 1.20 grams per milliliter. That's our density. Low-density lipoprotein, sometimes called bad cholesterol, is also measured in a routine blood test. If a 0.308 gram sample of LDL has a volume of 0.362 milliliters, what is the density of the LDL? So that's 0.380 grams divided by 0.362 milliliters, and that gives us a density for this LDL of 1.05 grams per milliliter. Osteoporosis is a condition in which bone deteriorates to cause decreased bone mass. If a bone sample has a mass of 2.15 grams and a volume of 1.40 cubic centimeters, what is its density in grams per cubic centimeter? Remember, cubic centimeters is just equal to 1 milliliter, so we can interconvert those terms freely. Density is equal to mass over volume, and in this case, our mass is 2.15 grams, and our volume is 1.40 cubic centimeters, which is equal to milliliters. And so that gives us a density of 1.54 grams per cubic centimeter, or 1.54 grams per milliliter. Greg has a blood volume of 5.9 quarts. If the density of the blood is 1.06 grams per milliliter, what is the mass in grams of Greg's blood? To work this problem, we'll need to convert quarts to milliliters, and then we can use density as a conversion factor to convert milliliters to grams. We have these equalities. 1 quart is 946 milliliters, and 1 milliliter of Greg's blood is 1.06 grams. So let's work this problem. 5.9 quarts times 946 milliliters per quart times 1.06 grams per milliliter gives us 5,900 grams of blood. The first term has two significant figures. The second and third have three each, and so we need two significant figures in our final answer. So our answer would be 5,900. During surgery, a patient receives 3 pints of blood. How many kilograms of blood of a density of 1.06 grams per milliliter were needed for the entire transfusion? In the previous problem, we see that 946 milliliters is equal to 1 quart. You might also know that 2 pints is equal to 1 quart. So we'll need to start by converting pints. Here we have 3 pints. We need to convert pints to quarts. Then we can convert quarts to milliliters. So we convert pints to quarts by 2 pints is 1 quart. We convert quarts to milliliters by 946 milliliters is 1 quart. Once we have milliliters, we can convert milliliters to grams using the density of 1.06 grams per 1 milliliter. Now we have grams, but we were asked to find our final answer in kilograms. So we'll need to convert grams to kilograms using the metric conversion factor. 1,000 grams is 1 kilogram. We're starting with 3 pints of blood. There are 2 pints in 1 quart. There are 946 milliliters per quart. We have a density of 1.06 grams per 1 milliliter. There are 1,000 grams in 1 kilogram. And we were asked to give our final answer in kilograms. Notice that pints cancels, quarts cancels, milliliters cancels, and we're left with grams. We'll need two significant figures here because we have two significant figures in our first value, and this one is unlimited. This one has 3, this one has 3, and this one is unlimited. So our final answer will be 1.5 kilograms. A woman receives 1,280 grams of type A blood. If the blood has a density of 1.06 grams per milliliter, how many liters of blood did she receive? We'll need to convert grams from the initial value to milliliters through the density. And then we can convert milliliters to liters through a metric conversion factor. So let's go ahead and get started. We're starting with 1,280 grams of the blood. This blood has a density of 1.06 grams per 1 milliliter. We know that 1,000 milliliters is 1 liter, and we were asked to give our answer in liters, so we're finished with this problem. We just have to put the calculation into the calculator. Our initial value has 3 significant figures, and therefore our answer is 1.21 liters.